All right, good morning, everyone.
Morning.
I'm Bob Fowler, representing the National Chemistry Week Planning Committee for the Cleveland section of the American Chemical Society. We're here this morning to demonstrate our 2013 program for National Chemistry Week. And this year's theme is Energy Now and Forever. As usual this year, we're going to have our hypothetical friends Millie and Avogadro join us. And when we told them that the theme this year was energy, since we're in Cleveland and we have a NASA research center here, one of the first things they asked was energy. What kind of energy does it take to get a rocket to the moon? So we thought what we would do today for our program was investigate several different kinds of energy and see if we could come up with, find out a kind of energy that would really be appropriate, both type and quantity, to get a rocket to the moon. And I'll give you a hint, we may find out that the best way to do it in the end is through chemistry. So let's get started with our program. Everyone has some latex-free rubber bands at their table. And when Millie and Avogadro were thinking about energy and forms of energy, one of the things they wondered was, well, is there any way a human being alone could power a rocket to the moon? And we were asking, well, what kind of things can a human being do? Well, a human being could take a rubber band and stretch a rubber band. And maybe by stretching a rubber band, there might be some kind of energy there, and it might help us get a rocket to the moon. So let's try it. Take your rubber bands and stretch them about 2 or 3 times their normal length, and let's put them against a very sensitive part of the body, our lips. And if you stretch them a couple of times, are these guys getting a little bit of a temperature difference? Maybe a tiny amount. As you stretch them and put them against your lips and then let them go, do you notice any kind of a temperature difference? Maybe a little bit of warmth. Well, all we're really doing is stretching some of the molecular arrangements inside this rubber band. We're not actually breaking any chemical bonds or anything. All we're really doing is creating some heat. And it isn't very much, is it? You can get a very slight warming sensation the longer, I think, and the more you stretch this rubber band. But it isn't a lot of energy involved. Heat energy in this case. You think there's enough energy there to get a rocket to the moon? Even if we did the old classroom trick of shooting a rubber band and attach it to a rocket, would that help us get a rocket to the moon? Probably not. So we can stretch it all we want, but it's not going to help us that much. Well, Millie and Avogadro had another idea. What about conversion of some potential energy? Everybody has what we call a racquetball popper at their table. They're just one per table, and we have 5 tables set up and labeled. What we did was we took some racquetballs and we simply cut them in half, actually a little bit more than a half. Because if you make them exactly a half, they don't do all that well. So what we'd like for you to do is impart some potential energy by turning the racquetball inside out, and then if you hold it very carefully, they're kind of sensitive, if you let them go onto a table, whoops, you got to let them go in such a way that they impact the table, bulge side up. Sometimes they work and sometimes they don't. Let me try it a third time.
2 points.
I don't believe it. 2 points right into the water. Well, as always, as good chemists, we're prepared. So we have some paper towels around here. And I think what I'm going to do is I'm going to turn this over to the troops and let somebody else have a go and see if they can get there. Everybody put their goggles on, please.
Well, yeah, we
Good
need a
chemist
couple
needed.
more pairs of.
Turn it inside out and drop it. Whoop. They're pretty sensitive, aren't they?
Yeah. If you can go to the tables and pass 2 up to that corner, we weren't planning anybody up there.
Is anybody else getting them to work?
I mean, it's easier if you just set on the table, and then eventually it goes down on its own. It'll, I mean.
Oh, yeah, that one.
There you
There
go.
you got one. Way back there working great.
That's looking pretty good.
Probably a pretty good reason to keep these water cups up on the demonstrator's table while you're actually performing the demonstration at the libraries. All right, now the question is, that potential energy got converted into kinetic energy pretty easily once we figured out how to do it, right? Is that enough energy to get a rocket to the moon? Probably not. Probably not. We need a lot of energy to get a rocket to the moon. As a matter of fact, we have to get up to a velocity called the escape velocity to free ourselves or free a rocket from the Earth's gravitational pull. That's like 25,000 miles per hour. So it takes a lot of energy to get there, and probably the racquetball poppers aren't going to do us. By the way, I've been lax in introductions and acknowledgments. Like to introduce Lois. Like to introduce Lois Kuhns and Margaret Pafford. Anyone else? Dr. Wayner, Mark Wayner. Anyone else here on the committee? Okay, on the planning committee. And really would like to express our appreciation to John Carroll University for allowing us to use this wonderful facility twice. Once to put our kids together, and then once today for the demonstration. And Dr. Wayner and Dr. Nichols, who have really helped us a lot. Mark, we really appreciate your help. Okay, let's try something else that is a form of energy. This time we're going to look at static energy. Million Avogadro, we're looking at some static tubes. We've simulated a static tube with just a water bottle with some styrofoam beads in it, and we're going to see if we can do anything with static electricity. Now, I am not going to do this, but all you guys back in the back, if you'll rub this thing well against your hair to impart some static electricity, and see what happens to the styrofoam balls. Come on, you really got to rub it really good. You really got to get some static electricity. Like you're rubbing a balloon, and you're going to stick the balloon on the side. Okay, what happens to the balls? The balls want to stick. Why is that? With static electricity, we're actually rubbing electrons off, and the tube is actually attracting the styrofoam balls. If you'll now take your finger and rub it where those little styrofoam beads are, you'll discharge the static electricity, and they'll fall away, and they'll go back into the main part of the bottle. Everybody okay with that? Okay, that's a demonstration of static electricity. It's the same kind of electricity that you generate on a carpet if you rub your feet against the carpet, or even lightning is a form of static electricity. But is the electricity in the volume, if you would, of electricity in this bottle, the static electricity, is there enough electricity in here to power a rocket to the moon? Probably not. Enough of an electrical charge to get the styrofoam beads to stick to the inside of the bottle, but probably not enough to do anything else. Well, you know, at this point, we were talking to Million Avogadro, our hypothetical friends, and they heard a cell phone ring, and they said, what powers a cell phone? Well, batteries, and in some cases, we can use sun power. We can use solar power. So we decided to look at the possibility of using solar power to power the rocket to the moon. Everyone has on their table some little devices. Sometimes they're Halloween devices, sometimes they're little plastic flowers, and everyone, except this table, which now is in business, everyone has a power source. Now, table 5, back in the back, doesn't have a power source, except what you do have is you have the lights overhead, and we have 2 flowers in the window over there, which presumably the solar panels on that little flower, both of those little flowers, are absorbing some photons from outside. So what we'd like for you to do is take your power source, whether it's a flashlight a big flashlight or a little flashlight or an LED or whatever you might have, or this desk lamp, and put your little solar array with your device under your power source. And does everybody have one that works? We had a lot of difficulty with these things. Half of them that we ordered came in and they weren't working at all. Something about a magnet or something isn't attached or whatever. What we'd like for you to do is, once you've got them working, we would like you to, I'm going to time like 30 seconds, maybe a minute. I'm going to time a minute, and I'd like for you to actually count the number of flaps, if you would, that your device does as you hold your power source to it. Or if someone wants to count the number of flaps, it's barely moving, the flower on the right over there. Someone wants to count that one. Let's see which power source gives the most flapping of whatever device you might have. Okay? I'm going to give you a count, and we'll count it for a minute. Please count the number of flaps as you hold your power source to your device. Ready, set, go. Okay, we've got 5 seconds left. 3, 2, 1, bingo. Okay, we're done. Okay, did anyone have over, say, 25 flaps? Several people had over 25 flaps. How'd this one do up here?
I got
130? Anybody else have over 100?
110.
Okay.
150. This guy's going on spiritual power here. And he's going to town.
It must be the photons from up above. Lois mentioned a second ago that half of these little devices, in particular the little flowers like on the table here, when they came in, they were dead on arrival. So I went over to a dollar store yesterday over near where I live in Seven Hills, and I actually took one of these little mini flashlights with me, and I walked in. They've got these things for $1, and I actually checked them out on the way to make sure that I got some that worked, okay? So the little Halloween guys, I see one back here still going crazy, and
Well, he's going
the
nuts,
skeleton's still
yeah.
going crazy too, huh?
He's
Okay.
been this way since we walked in. It's this like right here.
It's just the photons from up above. Of course, what we're getting is we're getting electricity to power these little devices from the solar array, from photons from whatever power source or whatever light source we have. At the molecular level, it kicks out electrons and actually makes an electric current, right? So that's what's powering these little guys. And you had 150?
Something like that. It was a lot.
So 150 flaps seems to be the record, huh? So it's amazing, even though some people were holding a light source directly, like a flashlight, directly on the solar array, what ended up happening was just the lights from the room probably win the Skeleton Award this year, okay? Alrighty, now that's very nice. But are there any issues with solar electricity that would prevent its use from powering a rocket to the moon? Well, what happens if it's a cloudy day and you want to get your rocket to the moon? You've got a problem. No, there are solar cars that exist, but they're very, very heavy and they don't work too well on cloudy days. And the other problem, I guess, is that can you really get enough electricity to really power a rocket to the moon? Probably not from a solar array. Now, interestingly enough, NASA is using and has been using solar arrays for quite a long time to generate power in space. When you think about it, if you need power on a satellite, unless you've got an extremely long extension cord, you've got a problem. So NASA actually uses, everybody has seen these satellites that the wings, quote unquote, unfurl as the satellite gets up into orbit. Those are the solar arrays, and depending upon the actual surface area of the solar array, depends upon how much electricity you can generate. And these days there's a whole field of study over at NASA called electric propulsion, where people are using the power from the solar arrays. There isn't much, but if you use what little bit of power there is over a period of time, you can generate a little bit of thrust. And people are actually powering rockets, or satellites I should say, once they're up in orbit, they're using that power to keep the satellite in orbit, or possibly sometimes even to move further into space. So there is some use for solar power, but probably not to get a rocket to the moon. Okay. Well, Millie and Avogadro, when they heard that cell phone ring, first thing they thought of was not a solar-powered battery, but an actual battery. So we thought we would take a look at the possibility of using a battery to power our rocket to the moon. Everyone has a lemon, a funny-looking lemon in front of them. It has 2 galvanized or zinc-coated nails inserted, and it has a penny. Of course, we've got a zinc copper possibility for a battery. But what we're going to do is everyone has 2 alligator clip wires, alligator clips on both ends. And if you look carefully on your table, you have, I can't even pick it up myself, you have a tiny little LED, light emitting diode. Now if you'll look at your LED carefully, on one side there's a flat spot. And also the lead on that side is slightly shorter. Okay, if you would note which lead, that's the negative lead, the one on the flat side and the one that's slightly shorter. What I recommend you do is take your LED, hold the 2 connectors like so, and maybe bend them out so that the whole thing resembles a big letter T when you're done. That way you'll have an easy way to connect on to the LED's leads. Okay, if everyone would now connect one of the alligator clip leads to each side of the LED, just connect those and make sure that they're separated, they're not touching or anything. Then what we'd like to do is see if we can generate enough power from the lemon battery to light the LED. Now, I have to tell you that the LEDs are almost impossible to see lit. It's almost impossible to tell when they're lit if you look at them from the side. So what we're going to do is we're going to dim the lights in a second, and then to test the LED to see whether or not it's being illuminated, you're getting enough power from the battery, look at the end. When you think about it, that's the way you see an LED in a device anyway. So look at the very end, don't look at it on the side. So now what we'd like is take your connectors and hook one to each of the 2 nails. And we're going to experiment a bit here. We're going to experiment in 2 ways. We're going to try to see if there's enough power to light the LED, and we're also going to be looking to see whether or not individual combinations, and we'll see what we mean by that, of electrodes, which is what those metallic devices are, work to light the LED. Okay, everybody got their 2 nails connected to the LED? Okay, Lois, if you would, please. Yeah, let me kill this little light too. Thanks, Margaret. Does anybody have any indication of the LED lighting?
No.
Okay, Lois, if you turn the lights back on. Okay, let's now disconnect the lead from the nail furthest from the center and hook it again. I'm talking about the nail way over here. Take the nail connector from this one and connect it to the penny. There's just enough of the penny to grab onto. Okay, Lois? Everybody got theirs connected? So now we've got the middle nail connected to the LED, and we've got the copper penny connected to the LED. Does anyone see any indication of the LED lighting? No, still not. Okay, Lois. What we're going to have to do is we're going to have to join forces. And when we join forces, what we're going to do is we're going to see if maybe if we put 2 or 3 of these batteries together, can we make it happen? What I'd like to do is, yes, take the battery from table number 1, which you've done, disconnect the lead from the penny. Everyone, please disconnect the lead from the penny in tables 1, 3, and 5. Disconnect the lead from the penny. The people from table 1, they've already done that. Take their lemon back to table number 2. And the people from number 3, if you would take it in 3 and 5, take that to number 4. Everybody's going to, those 3 tables are going to number 4.
Vince had a very interesting mnemonic he came up with the other day, that the negative end is connected to the penny.
That's
or
right.
The nail, negative nail, positive penny.
Okay. Okay, now what we're going to do is we're going to have to very carefully reconstruct it. The people back at table number 4 aren't going to do anything just yet, okay? If you want, you can come over here to table number 2 and watch what happens at table number 2. All right, now what we're going to do is we're going to use one of the LEDs. So disconnect, table number 1, people disconnect their LED completely and leave it, okay, there you go. And you can take the second lead and put it back on table number 1 as well, that green lead. Get rid of that one. Okay, now we're going to make sure that, well, here's what we're going to do. We're going to take the nails and we're going to connect the middle nail from number 1 over to one of the nails. Leave that alone. Okay, connect that other to the other nail on number 2. Now connect the lead from number 2's LED to the other nail on number 1 battery. Okay, Lois, if you'd kill the lights.
Oh, Mark's got it there.
Mark's got them, okay. Any indication of anything lighting on the LED?
Doesn't look like me.
Okay, if you would, Mark. Now what we're going to do is we're going to disconnect the cables from the outer pennies, not the middle penny, but the outer penny, the one furthest away from the center.
You mean the nail?
The nail, I beg your pardon, from the nail, yeah. Okay, and now we're going to put these things in series. The first thing we want to do is make sure that this nail on lemon number 2 is connected to the negative side. Is it connected to the negative side of the LED, the short wire, and the side with the flat?
The white one is shorter.
This one, yeah, that's right.
Okay, then you're going to have to change those around. Make sure that the nail on number 2 is connected to the negative. All right? Now, let's connect the nail to the penny over here on number 2. We're going to put the batteries, the lemons in series. Now we're going to connect that, the other side of the LED, to the penny over here. Whoops,
There you go.
Yeah, you can see it.
Okay, now we're going to try it again. Mark, do we have something? How about that? Okay, notice what's going on. First of all, when we tried the 2 nails a minute ago, even when we had the 2 lemons in series, did we get anything to light?
No.
No. So now what we have is we have nails used for one electrode, and we have pennies for the other. So we have 2 dissimilar metals, and now we in fact have almost enough power, well we do have enough power, to light the thing. Okay? Okay, you can disconnect that one from that one.
Like,
And let's light Mark if you would, and let's go over to the final table. And let's connect these 3 lemons nail to nail, if you will. We only need 1 LED here. Okay, we'll just use 1 LED, and let's go from there. We're going to use nail to nail, and we're going to try 3 lemons using just the nails. Let's connect nail to nail. These things are a little bit slippery at times. Okay, and let's connect that nail across the LED.
I'm gonna take a photo and then I'm.
Where's the LED?
Here,
Okay,
okay, wait a minute.
we're good. Connect that to the nail. Okay, nail to nail, and
Step
hook
back
that
for a
to the
moment. I
LED.
wanna take a
Okay,
photo of this.
Mark, where's our,
I'm gonna get
our light
it
person?
instantly, right now, okay.
Okay, now we've got 3 lemon batteries connected in series, but all we're using is the galvanized nail electrodes. Is there any indication of any lighting?
No.
Okay, disconnect the LED completely, if you would, Lois. Let's have the lights one last time. Now we're going to connect 3 batteries in series. Okay, let's take the batteries and connect them middle nail to the next one's copper penny.
Hold still.
Okay, nail to penny, nail to penny. If I can get the silly thing off, there you go. Nail, and use the middle nail each time. Nail to penny, nail to penny. And then make sure that the nail on the last one is on the short lead of the LED. The one that's connected to the flat side.
Which one's the flat?
There's a little flat side on the LED. Can you find the flat side and the shorter of the 2 leads?
I'll take a photo
Okay,
and
here's the
I'll
flat side.
turn off the lights.
Okay, the
Nails
nail
first.
is connected to that one. That's the negative side. And now finally, okay, let's have the lights. Are we all set here?
It's on.
All right, Bob.
It's not as strong as the last one.
It's
Not as
barely
strong.
on. Yeah, it's barely on.
Well,
Maybe,
it's on, but it's barely on. We must have a little bit of a bad connection there someplace. One of the things that we need to make sure of when we set this thing
Yeah,
up
you just
for the
have-
library demonstrations is to make sure that all of the nails and all of the pennies are in snug and not loose.
and
if
then
they're-
roll
I can see
the
it now,
lemons
full
ahead
thing.
of time.
Oh yeah, I forgot
Get
to
the
tell you
juice
that.
that. Juice them.
Okay, well, actually in tests at home,
Oh, it's on better now.
okay, so you must have a better connection then.
Yeah.
Hit the lights one more time, and I think we have a little bit better connection. Yeah,
This one up here is doing okay. Not major, but
well, this one's only 2 batteries,
not 3.
2 lemons rather. This one is 3 lemons. This one should be a little bit lighter, so we've got a bad connection somewhere, okay? But you get the idea. As
There,
long,
that helped. That helped.
is it better now?
Yeah.
Okay. As long as we have nail to penny, and in the end, we have the final nail to the negative side of the LED, we should get a good circuit and a good connection. Okay? Okay, let's disconnect those. I think we made the point that we can, in fact, generate electricity with a battery. Now, a couple of points to make clear to the students at the demonstrations in the library. First of all, anytime we used only nails as the electrodes, what happened? Nothing happened, of course. We need 2 dissimilar metals to create a cell. Since we tried using 2 nails, even with 2 and 3 lemons. I'll put those back on in just a second. And even when it didn't light with 2 nails and the lemon, but it did light when we used a nail and a penny combination, 2 and 3 different lemons. That says 2 things. It says, first of all, we need dissimilar metals to create a cell, of course. And secondly, the lemon itself is not the source of the potential. Some people might assume that the lemon is the source of the potential. It isn't. The lemon, of course, with citric acid in it, is simply the electrolyte. And it's the 2 dissimilar metals, the galvanized nail, which is zinc, and the copper penny, or copper-coated penny these days, do form an actual cell. Now, one thing that you really need to do at your demonstration is read the script a little bit. It tells you 2 things: you have to buy some fresh lemons just before your demonstration, and what you need to do before you insert any electrodes is roll the lemon. That breaks the membranes to some extent on the inside of the lemon, because remember, we need the electron flow through this thing, and if we could have just a pool of citric acid inside, that'd be the best thing. But failing that, we need to make sure that we have an easy flow of electrons, and the membranes impede that. So break those up by rolling it really, really well on the table before you insert the electrodes. Okay,
You know what, I have one other suggestion.
certainly.
Rather than telling the kids the nail in the middle, the nail on the side, if maybe you wanna take a Sharpie on the lemon and make a mark on that middle nail, so you could tell them the nail with the mark versus the side, because then you're gonna be telling them which nail and walking around the room. And just on the lemon, so you're not messing the nails when they touch it,
Okay,
And
that's a
that
good
way you
idea.
could say that the nail with the mark or the circle around it or something, and denote it that way.
Okay, I think what we could do then is, what the script tells you to do, is it tells you, I don't know, Austin, if you can see that on this, because I've already punctured the lemon. It tells you to put a dot here with a magic marker, a dot right in the center, longitudinally if you would, and then a line right here. Cut the line with a paring knife so you can insert the penny, and then put nails in the 2 marks. Maybe put a little circle there instead of a dot. And so you could say, okay, use the nail with a little circle around it, rather than the middle nail or the outer nail or whatever. Good
Because I
idea.
think they'll be confused.
Good idea. Okay, so we actually,
You'll see that it's gotten much brighter.
oh yeah. As a matter of fact, the script mentions that the penny will get cleaned as it's immersed in the citric acid. Okay, we created a battery, and we saw that we can actually make batteries with a lemon, and they actually work. Well, with 2 lemons at least. Do you think that batteries and battery power would be sufficient to get a rocket to the moon? Probably not. Probably not. Since you'd have to have even a big bank of batteries to power even an electric car. So to get a rocket to the moon probably isn't going to happen. So now, Billy and Avogadro were thinking, well, maybe the answer to get a rocket to the moon isn't these other kinds of power at all. Maybe we need to look at the power of a chemical reaction. So the next thing we're going to try is we're going to see if the mixing of a couple of chemicals might provide enough energy of the right kind that we could use to get a rocket to the moon. So everyone, most of you at least, you guys don't have to share, have a paper plate with some powder in the middle, sodium polyacrylate, and what we're going to do is you have a glass of water, and you know what's coming probably. We're going to pour the water into the cup, and we're not going to do anything else except watch what happens when we pour the water onto the sodium polyacrylate. So go right ahead and give it a whirl and see what happens. Pour it all in, and we'll let her rip. The kids love this one. And as a matter of fact, if anybody wants a little extra water, you want a little extra water? More water? Well, it will only absorb so much water. Well, you guys have got a nice snow cone over here. Some more water, anybody? Okay, well, you get the point. What we like to do now, once the absorption has finished, turn the cup over and very gently dump it onto the paper plate. And now, take your hand and slowly put it on top of the expanded powder. And what do you feel? Don't tell me you don't feel anything, Margaret. What do you guys feel? Anything?
It's cool.
Yeah, it actually has cooled down a little bit. Okay? We think there was a heat of absorption in there at first, probably when the material absorbed the water. Great stuff, isn't it? It's artificial snow, of course. And once the water starts to absorb, you have water on a huge surface, so you've got a lot of surface for evaporation. So you get a little evaporative cooling, and you get a cooling effect. So there is a little bit of energy involved. But is it really enough energy to power a rocket to the moon? Probably not. Okay, well, let's go for the ultimate, and let's use a chemical rocket directly. I'm going to come around with some Alka-Seltzer tablets and give everybody an Alka-Seltzer tablet. Lois, do we have any more of the little vessels we can use for the rockets?
Yeah, how many more?
Is demonstrate to the students. Go ahead. Will I pass them? Of course. Oh, you guys need some Alka-Seltzer tablets. Okay. Apparently not.
Why don't I put one on the table, right?
Okay. Demonstrate to the students the proper way to do this. What the script says is let's do this table by table. Now over here, we have a little tray, and everyone should, with their kit, take one of these little trays. And if you're in a library, you're probably going to have a carpeted floor. So these little guys, and the poppers, by the way, as well, might not work very well on the floor, and maybe they don't want to use them on the table. So you can put this down as something solid that you can use as a launching pad for our little chemical rockets, or you can use it for dropping the poppers onto, or what have you. What we'd like for you to do is show the kids, first of all, tell them not to do anything with the Alka-Seltzer tablet until you tell them to. Then take them table by table, take one table back to the launching pad, and then demonstrate to everyone the proper way to do this. First of all, these are the caps that fasten on the inside, not over the outside. So they'll come off fairly easily. We want to make sure that what the kids are going to do is not fool around with these things, but they need to put the Alka-Seltzer tablet in when you tell them to, table by table, put the cap on immediately, and have them practice before you put any Alka-Seltzer tablet in the water. Have them practice taking the cap on and off a couple of times, because you know what's going to happen when you give them the Alka-Seltzer tablet. They're going to fling it in there, half of them are going to drop them probably, and they're going to fiddle around with this cap, and oh, I can't get my cap on. So have them practice it a few times, okay? And once they know what they're doing, as they're lined up, table by table, you take the first table's kids, give each one of them a tablet, tell them not to do anything with the tablet until you tell them. Then they're going to drop the tablet when you tell them to into the water. They're going to put the cap on. They're going to turn it upside down and put it on the launching pad. And hopefully, you don't even have to shake it. Boing. Now what happened was we're only using about a quarter of an Alka-Seltzer tablet, so we're probably not going to blow the lights out in any of the libraries, hopefully, okay? So you guys want to actually try that yourself? Let's go table by table. Table number one, come on over. Come up to the launching pad. Come on down. You can come too, Margaret. Mark, whoever. Okay, now remember, hold on to your Alka-Seltzer tablet. Take the cap off. Practice taking the cap on and off a couple of times. Don't drop the Alka-Seltzer tablet in until we tell you. Everybody okay with the cap taking it on and off?
Yep.
Okay, if you're ready,
Put it down.
when I tell you, put the Alka-Seltzer tablet in, put the top on, and turn it upside down, and sit it on the launching pad. And stand back. And make sure at this point, please, that everyone's wearing goggles. And don't let the students, don't let them approach the rockets until they pop. if anyone approaches the rockets because they haven't popped for some reason, after about 30 seconds, let it be you, okay? The last thing we need, boing, there we go. They're all gonna pop eventually, it's inevitable. That's because we have enough Alka-Seltzer and because we have those internally fastening caps, okay? So if anybody has to go up and check it out, let it be you. And make sure you're wearing your goggles. Okay, next table, come on. Hopefully we can confine the mess to the launching pad.
Looks like it's actually contained. It's first. Ta-da!
Did you get that on film?
Not 2 points, you didn't land it next.
That's as good as the popper going into the water.
A little piece of
It's gonna happen. Okay, is that the last of them? Okay, last table, please, come on down.
Not yet.
You wanna hang on to these?
We're gonna let the kids take them in the end. Okay, everybody okay with flipping the caps on and off? Okay, everybody come up to the launcher and go ahead and drop your Alka-Seltzer tablet in, get the cap on, sit them upside down, and let's do our thing.
I didn't see the little
That one's even moving a little bit. Oh. Okay, as you see, with maybe 1 or 2 exceptions, there really isn't enough Alka-Seltzer in there to blow the lights out at your libraries. And hopefully, this little launching pad will contain most of the liquid. So it's just water anyway, a little CO2 at this point. So it shouldn't be a problem for your libraries. Okay, we're pretty much completed in less than an hour. And I realize that all of you guys are experienced chemists or scientists, so you pretty much know what you're doing. And it may take a little bit longer with the students, but still it looks like within an hour or so, you ought to be able to complete everything that you need to do. The last thing that I would tell you is the librarians are all going to have sign-up sheets. And I would recommend that you use the librarian's sign-up sheet. When you get to the library, of course, you want to introduce yourself to the children's librarian. That's the person of consequence. And make sure that they bring their sign-up sheet to the demonstration. And then at the end, you'll have 5 or 6 of these things. And maybe use the order in which the kids signed up to pass these out. Okay? So kids number 1 through 6 or whatever, get these things. Then, they're all over the place. We have some little plastic bags that were included with Experiment 6, or with Experiment 5 rather, which is the lemon battery. What you can do is you can go around to the various tables, collect the wires, put them in the bag, and then give them to the next 5 or 6 kids, and they can take these home and use them at home. They can also take their film canisters with them, and since there's 1 racquetball popper per table, again, go to the sign-up sheet, and maybe kids, 13 to 18, whatever, will get one of the poppers. So hopefully, all of the students coming to the program will get some kind of popper. 2 last things. In your kit, there is a manila envelope And the manila envelope has in it a couple of things. It has, first of all, a feedback form for you. If you could complete this and include it with your box of goggles. We're going to give each of you a box of goggles and a kit. That the goggles, for sure, need to be returned back to us. They're already pre-labeled for return through the library system. All you have to do is give them back to the librarian. If you would put this sheet back into the envelope. You also have some student feedback forms. If you'd ask, and little pencils, each of the students will have one of these that you put out originally, or you can wait till the end if you like, and they'll have a pencil. So if each of the students, if you'd ask them to fill out a little feedback form themselves, we'd appreciate that. You also have in here some photo consent forms. As the parents come in, if you plan to take pictures, remember two things about pictures. Number one, everybody needs to have goggles on when and if you take pictures. Everyone. ACS is, that's a demand from ACS, that everyone wear goggles in a picture. And number two, obviously there are going to be cases where some of these students' parents object to the notion of their children being photographed. So ask the parents on the way in, maybe have a little setup table where you have the goggles on the setup table and these forms on there. Ask the parents for permission in writing to take pictures of the kids. In many cases, the libraries will have their form as well. In that case, I recommend that you have the parents fill out both forms. And lastly, there's a handout sheet that again you can put up on the front table, but I'd recommend that you wait until the end to hand these out. NASA prints our script and most everything for us every year. They were nice enough to actually print these in color this year, so they look pretty good. So give each one of the kids one of these things. It goes into a little more detail about hamburgers, how many calories are in hamburgers, the fact that people get their energy from the food that they eat, and since you have about 250 calories in a hamburger, that gives an individual enough energy to play racquetball or soccer for about an hour. So you can use that as sort of a metric in terms of the overall energy numbers that we're talking about. There's also information on here about the number of calories in a gallon of gasoline, again, for a metric to measure things against. And it turns out that the number of calories in a gallon of gasoline, I think is like 31,000, is that right? Kcals, I believe. And that's the equivalent of about 125 hamburgers. And to put the whole thing into perspective, that the students will understand, I think we can dispense with these at this point. We're finished with them going into the program. Don't step on the launching pad like I just did and spread everything all over the place.
I have one other suggestion.
Certainly, please.
I like your suggestion of handing out the stuff, but I think rather than telling them what you're giving them, let the first 5 kids choose what they want, like package everything, so then you don't have the negotiations afterwards of, oh, I would rather have this, or I would rather have that, and they won't fight as much because they know the first kids get to pick.
She's talking about these things, the racquetball poppers, the bags of wires.
Just have them in piles, and the first 5 names
Very good.
some can say,
Can come up
which do
and
you
take
want to
5.
pick
Good
one
idea.
thing, and that way the kids that signed up last just get what's left.
Good idea. And your script has all the details in it, but each kid can take home their static tube as well as their rubber band and distribute the poppers, the flowers or the little solar powered devices, and the wires according to that. That was a good suggestion.
How about the diode?
I would put that in the bag with the wires.
With the wires.
Yeah. So that way a kid, if mom goes
Has
out and buys
everything.
some lemons and dad probably has some galvanized nails lying around, they can repeat the experiment at home. Of course, they always have pennies. One last comment I'd make to you. Any idea, can anybody give me a wild guess as to how many equivalent hamburgers it would take to shoot a rocket to the moon, to escape the Earth's gravitational field, to achieve that escape velocity of 25,000 miles per hour?
More to make it even less.
Hundreds of millions?
I bet McDonald's wants to make that one.
I bet if you look at the McDonald's sign, they've made more than that. You know, they always have 10 zillion hamburgers made.
Billions and billions.
3 million hamburgers, roughly. 3 million hamburgers worth to send a rocket to the moon. I would suggest you read the script, of course, for all kinds of reasons, especially for the setup. Don't forget you need to buy 6 lemons beforehand. And look at the list of things that you need to bring along. I think it's on page 9, but wherever it is in the script. Make sure you have all the equipment that you need before you leave home. And one last thing I would suggest is wait until, well, there's 2 schools of thought on this. Either wait until you get to the library to put your lemon together. It doesn't take that long, really. 3 or 4 minutes and you're done. Or put them together at home. If you put them together at home, I would imagine that some of these are going to leak some lemon juice, some citric acid. So if you have to do them, if you think you want to do them at home, to save a little bit of time at the library, maybe put them in some kind of a gallon bag or something like that, so they don't drip all over your kit. Lois and I set everything up this morning in well less than an hour. So the setup time this year is nowhere near as onerous as it has been in past years. So I think if you get there at least an hour in advance, introduce yourself to the children's librarian and go ahead and set things up. Try to get an assistant if you can. That works wonders if you have an assistant, both to help set things up and to help you during the program and to help you clean up at the end.
Goes so much more smoothly. Goes so much more smoothly.
It really does. Rather than trying to think of everything yourself, kind of tell your library assistant what's going on, explain the program to them a little bit, and they can really make a world of difference in their presentation. Okay, any questions, guys? Okay, that's it for this year. Thanks for coming, and good luck with your presentations out there in the big bad world. Thank you.
Thank you.
Thank you.